What is the piezoelectric effect? The piezoelectric effect is the ability of certain materials to generate an electric charge in response to applied mechanical stress. This effect is reversible, meaning that materials displaying the direct piezoelectric effect, the generation of electricity when stress is applied, also demonstrate the opposite piezoelectric effect, the generation of stress when an electric field is applied. History of piezoelectricity. Brothers Pierre and Jacques Curie, as shown in the picture below, were the first scientists to see the direct piezoelectric effect in 1880. They used Rochelle salt, cane sugar, crystals of tourmaline, quartz, and topaz. They found that pressure applied to a quartz crystal creates an electric charge in the crystal. Research has been performed into the development of materials with improved piezoelectric properties, enabling commercial utilization of the piezoelectric phenomenon. This effect is still in many everyday uses, such as cell phones, diesel fuel injectors, acoustic guitar pickups, grill igniters, ultrasonic transducers, vibration sensors, certain printers, and even musical greeting cards. Piezoelectricity and ultrasound. Medical ultrasound utilizes the piezoelectric effect through the use of a crystal within the transducer. The piezoelectric crystal in the transducer converts electrical energy into mechanical vibrations, which creates a mechanical wave which is reflected off of the object being interrogated. The mechanical wave then returns to the transducer crystal, causing it to vibrate. The mechanical energy is then converted by the crystal into electrical impulses. By measuring the time between when the sound was sent and received, the amplitude of the sound, and the pitch of the sound, a computer can produce images, calculate depths, and calculate speeds. During the early stages of the transducer design, the most common materials used were Rochelle salt, cane sugar, crystals of tourmaline, quartz, and topaz. As of today, in the transducer ultrasound crystals, PZT is the most common material, which stands for lead zirconate titanate. The piezoelectric effect is commonly utilized today. In the automotive industry, airbag sensors, airflow sensors, audible alarms, fuel atomizers, keyless door entries, seatbelt buzzers, and knock sensors are all used. In a computer, disk drivers and inkjet printers are also using the piezoelectric effect. For the average consumer, cigarette lighters, as utilized in our experiment, depth finders, fish finders, humidifiers, jewelry cleaners, musical instruments, speakers, and telephones all are using the piezoelectric effect also. In the medical field, disposable patient monitors, fetal heart monitors, and of course, ultrasonic imaging utilizes piezoelectricity. And in the military industry, depth sounders, guidance systems, and hydrophones and sonar are all being used in the piezoelectric effect.
The piezoelectric effect is the ability of different materials to create an electric charge in response to applied mechanical stress. When piezoelectric material is under mechanical stress, a shift in the positive and negative charge occurs, which results in an external electrical field.
You may be surprised that piezoelectric elements are found in everyday objects like lighters, watches, microphones, and speakers.
A lighter can utilize the piezoelectric effects by using the spark wheel. When the spark wheel is rotated at a sufficient speed, it creates voltage by the small hammer inside striking the piezoelectric crystal inside the device.
Once there is enough voltage, a spark is created and held up to gas and will ignite a flame.
This is an example of our lighter that we used in our experiment. This is a spark wheel here. This has the piezoelectric element, and when it strikes the element, it creates a flame. Come on, bud.
Yay!